All right. Hey, AP Chemisters. This is Mrs. Vanderlei bringing you 6.4 Part 3. I told you it's going to be a longer one. This is a really important section, okay? This is a really important section, okay? This is the thermal energy transfer, and it's the idea back of Q the system equals negative Q the surroundings. And it goes back to the idea of if energy is being absorbed by something, it's being released by the opposite. So if the system is absorbing energy, then the surroundings are losing energy. If the system is losing energy, then the surroundings are absorbing it. So their signs need to be different. Don't you dare drop that negative sign. That is so important. So this is handy because we're going to use the fact that water is slow to rise in temperature so that we can maybe heat something up pretty hot, throw it in some water, and the temperature isn't going to change by that much, okay? And so we can measure indirectly things that you can't just stick a thermometer on, okay? Like a chemical reaction, it may be a little more difficult to find out how much energy is released by a chemical reaction. If you want to burn something, you're not going to stick your thermometer in the flames because it'll probably ruin your thermometer. But if you have that energy from the burning, the combustion, go into a pot of water, then you can calculate the Q of the other system if your surroundings is your water. So we're going to start off kind of easy. Suppose a block of metal is initially at 55 degrees, is submerged into water initially at 25. Thermal energy transfers as heat from the metal to the water, so from the hot to the cold until they're both at the same temperature. That's called thermal equilibrium. They're gonna, if you know the mass of the block, if you know the mass of the water, you know the Q of the block, you know the Q of the water, you can calculate whatever you need to, knowing that setup where one thing is giving its energy to the other, and you set up the equation. So problem number 13 is exactly what we're doing. We take a 32.5 gram a cube of aluminum, starts off kind of warm at 45.8 degrees. You put it into 105.3 grams of water at 15.4 degrees Celsius. What is the final temperature of both substances at thermal equilibrium? Okay, so this is probably one of the hardest type of problems to solve for when we're solving for TF of both, okay? So what I do, this is how I do it to help me be more organized. I start off with this. Q system is negative Q the surroundings. So I'm going to replace Q as MC delta T, and I'm going to make aluminum always on the left side and my water on the right-hand side, because this is my system and my water is the surroundings. It's surrounding the block of aluminum. And what did I not forget? I did not forget my negative sign, right? So let's check this out. How much aluminum do I have? I have 32.5 grams. What's the specific heat capacity of aluminum? I looked it up. Oh, there's a chart someplace, and there it is, okay? I do not know my final temperature. That's why I have it there, okay, is TF. Then I have my equal, and I did not drop my negative sign, so I shouldn't expect you to do the same. What's the mass of the water? They told me it's 105.3. What's the specific heat capacity of water? Hopefully you haven't forgotten that. You're going to get used to it. And final temperature minus initial, okay? So now how am I going to go about doing this math? Well, do you remember how I did it before? I ended up multiplying these two numbers together, and I got 29.3, and I keep this here. And then here's my equals, and don't forget your negative sign. And then I multiplied these two right here, and I got 441, and then I just brought this here, okay? So at this point, it's just algebra, but as I've been teaching this for a long time, I know that the algebra gets messy for some folk, all right? Be very diligent and make sure you know what you're doing and you don't drop signs or things like that. And I'll kind of help you as to how do you know if your answer makes sense or not, okay? So what did I do next? I'm looking at 29.3 and negative 441. Your smaller number is 29.3, so I'm going to divide both sides by 29.3. So this drops out, so that's all I have left. And then what's negative 441 divided by 29.3 is equal to negative 15.1. Okay, and then I have this here again. So now this just becomes pure algebra. If you want to stick x's where the TFs are, that, you know, do whatever. But now I would distribute this. Okay, so here's this. So it's equal to, so negative 15.1 times TF. And what's negative 15.1 times negative 15.4 is positive 232. So now what am I going to do to both sides? I'm going to add this to both sides, and that gets me 16.1. I'm going to add this to, whoops, well, I'm sorry, just the 45.8 to both sides, and I'm going to get equals 220 or 277.8. And then if I scroll down just a tad, divide both sides by 16.1, TF is equal to here, whoops, but what about my sig figs? How many sig figs should I have? If you go back and look, I think you're going to end up with 3. So that's what I got. Let me show you something. If I were you, I would jot this down as well. Okay, I'm going to scroll down here. So I have a graph here. This is temperature, by the way, and this is time over here. And what temperature did water start off at? Do you remember? It was at 15.4. Go back and look that up again. And what temperature did aluminum start off at? It was at 45.8. And what happens when that hot aluminum goes into the water? Notice the temperature of the aluminum goes down. When the hot aluminum went into the colder water, what happened to the temperature of the water? The water went up. And what was the final temperature? It was 17.3. And does this make sense? Well, does it make sense that water goes down or goes up about a fourth of what aluminum goes down? Why a fourth? Because that's the differences in the heat capacity. So aluminum is losing a lot more heat faster than water is. It's because aluminum's heat capacity is much less than that of water's. I'm, guesstimate about 4 times or so. And so it should make sense that water went up only a little bit compared to that of aluminum. Okay, so that is what's happening here. So let's go on to the next page and see what we're going to do. All right, so a block of copper with unknown mass has an initial temperature of 65, so it's been heated. Copper is immersed in a beaker containing water, 95.7 grams of it. When the two substances reach thermal equilibrium, the final temperature is 24.2. What's the mass of the copper block? I think you all can do this on your own. So please, I mean this, pause this, work it out, and when you're done, does your answer make sense? Then come back and see how you did. All right, this is what I did. All right, I always write down my equation. Please get in the habit of doing that too. And then I substitute. So what am I talking about? I'm dealing with my copper. I'm dealing with my water. Don't forget your negative sign. All right, and now I'm going to start plugging in the values I know. I don't know the mass. That's what I'm looking for. I looked up the specific heat of copper. Here is my final temperature. Remember, delta T is always final minus initial, right? So here's my final minus my initial temperature of my copper, right? Equals, don't forget your negative sign. Here is your mass of your water. Here's that 4.184 again that we've seen a lot. Here's your final. Notice they're both at the same final temperature. There's a little check for you. Minus the initial temperature of the water. So look what happened. Did the initial final water went up? Initial final copper went down. That's the way it should be. Okay. So now what? Do your math. Okay. I went ahead and did inside the parentheses. I subtracted my temperatures first. Notice I have a negative here. All right, and I got a positive 1.5 here. But what will this negative and this negative right here do? They're going to cancel each other out. So then what did I do? I multiplied these two numbers together, and I got negative 15.8 times the mass is equal to, I multiplied those three numbers together, I got 600.6. I have a negative sign here, so my negatives cancel out, and so I have the mass of 38 grams. Well, only 2 sig figs, by the way, because when I subtract it over here, I subtracted my temperatures. What is going on? There we go. I got 1.5, which is 2 sig figs. Okay, so the mass of my copper block is 38 grams. Hopefully that makes some sense to you. All right, let's go on to the next problem. So why don't you read problem number 15, come up with an answer, and then when you're done, come back. All right, how'd you do? Well, notice if you set up your MC delta T, what they say? They said that mass A has twice the mass of substance B. So this mass is twice as big as this. All right. What else they say? The specific heat capacity of B is twice as big as A. All right, so notice what's going on here. So they kind of cancel each other out. So what's going to be true? Your delta T's are going to be identical. So the final temperature is actually going to be smack dab in the middle between the two. Okay. So the next section is work is force acting through distance. Remember how this whole chapter started out? Here, hang on, or this section started out. It says quantifying heat. That's what we've just been doing a lot of. Now we're going to quantify work. Okay, so let's go back to where we were. So on that first activity, remember I had you playing with that syringe? So the syringe is going up and down. That's that force acting through a distance. So we're going to find work as negative P delta V, where the gases are involved. They're expressed in joules or kilojoules. Now the problem is we're going to have to make this, I can't even think of the word right now. We're going to have to convert, there we go, these units at some point. So don't forget, 1 liter atmosphere is 101.3 joules. That 101.3 joules should sound familiar because that's your kilopascals. So like I said, remember, E of the system is Q plus W. Here it is again. And you always have to have a sign with the number. The sign will indicate into the direction of the flow. So the energy flows into the system by heat. It's called endothermic, which means heat within. And the sign is going to be positive. Oops, then why did I bring out the negative? It's going to be positive. If the energy flows out of the system, all right, it's called exothermic. All right, exo means out, heat, and your sign is going to be negative. If your system does work on the surroundings, that means it's going out, it's going to be negative. Come here. And if the surroundings does work on the system, W is positive. If you go back and look at like that second page that we did, you'll see we did that too, all right? Let's go to the next page. So when I have a case of work done by the gases, the piston was pushed up. So here's my initial volume. And that piston is going to push up. And so what's going to happen to that piston? It's going to increase. So your VF is up here. So your final volume is bigger than your initial. So what's delta V? Well, delta V is final minus initial, right? So let's say this is, 10 liters. My initial was maybe 5 liters. Well, what's 10 minus 5? It's a positive number, isn't it? So a big volume minus a little volume is a positive volume. All right, so what just happened here, delta V is positive, work is negative. So the equation, once again, is work is negative P delta V. If delta V is positive, there's always a negative sign in front that makes work negative. So what about the next situation? What about work is done to the gas? All right, so here's my example. So I have a 2-liter container, and then this is going to be pushed down. So now, oops, come back down here. There we go. So now I'm pushing down the syringe. See that? I thought it was pretty clever. And now maybe your volume is, let's say, 1. That's your volume final. I'll put volume initial up here then. And so what just happened? Final minus initial. All right, that's a negative number, isn't it? All right, so 1 minus 2, if you will, is a negative number. So delta V is negative, W is positive, and again, your work is positive. Why? Because it's negative P, negative delta V, negative and a negative make a positive. All right, so I thought I could finish it in 3. I don't think I can, so I need to go to a 4th one. It'll be a lot shorter though, and I apologize. So don't wait to be great. See you shortly. Bye-bye.